Hello everybody, this is the second video clip for section 4.6, okay, which is the directional derivative and the gradient vector. So what we are going to talk about in this video clip is the so-called tangent planes to the level surfaces, okay. So let your S be a surface, so it may be look like this, okay, depends on whether whatever surface that you're looking for, okay, and the equation that represent your S depends on x, y, z, okay, and the relation in terms of f equals to a constant k, okay, so it is f of x, y, z equals to k, okay. For example, the surface that you may familiar with is x squared plus y squared plus z squared equals to the r square, which is the sphere, right? Remember? And then let us pick up one of the point, okay, on the surface. So for example, somewhere right here, this is the point P at x0, y0, z0, okay, be the point on the surface is, okay. And then let's talk about the curve C, okay. So the curve C is any curve that is lying on the surface. So maybe this is the curve that we're talking about, okay. So this is the curve C, and then for the curve C, of course, it can be represented by the vector function RT, okay, which is xt, yt, zt, okay. So this is the all the three-dimensional coordinates, okay, on this curve, okay, along the surface, okay. So this means that the point P can be regarded as one of the point along this curve. We'll call it R at T0, which is the vector x0, y0, z0, okay. And because this curve lie on the surface, then it means that each and every coordinates on this curve must satisfy the equation f of xyz equals to k. But right now your x depends on t, your y depends on t, your z depends on t. So you are going to replace all these by f at xt, f at xt, and then yt, zt equals to k. So right now your f, the final variable, is a variable t, okay. So if you use the chain rule, okay, to find a derivative, what we need to find is a derivative with respect to t, okay, and you are going to find a derivative with respect to t both sides, okay. On your right hand side it is a constant, so a derivative becomes 0, but on your left hand side, because you got three component first, so each of the component, for example, it will look like this diagram, right? The f of x, y, z, and then each of them depends on the t. So it is the derivative of f with respect to x, and then dx by dt, and we use a straight d because this one contain only one variable. And then the derivative of f with respect to y, dy by dt, derivative of f with respect to z, dz by dt. So all these three terms is the contribution of your df by dt on each of the component, okay. So it means that these three terms added or combined together equals to 0, and this one actually it looked like f sub x, f sub y, f sub z as a vector, and then dotted with dx, x prime, y prime, and z prime as a vector. Is it? They look alike, just like this, because they are pretty much the same using a dot product, okay. What is this one that we have learned before? This one is the gradient of your f, okay, and this one is actually, for this one, x prime, y prime, z prime, is actually your small r finding a derivative, right? So here from this relation we have the gradient of capital F dot with your r prime equals to 0. And what does this mean? This means that especially at this particular point, okay, t0, or at the coordinate x0 y0 z0, your gradient at this point dotted with the r prime at this point t0, it equals to 0. So it simply means that the gradient vector, okay, the gradient vector at this point p is perpendicular, right, or orthogonal to a tangent vector r prime of any curve, okay, of any curve c on the S that is passing through point P. Okay, so this means that what we have is the tangent vector, right? This is the, so this one, your curve is small r, the tangent vector will be your r prime, okay, and then the one that we talking about is the one that is perpendicular to your r prime, which is the gradient of f, okay, at this point, okay, at this particular point. So if we can find some vector that is perpendicular to this kind of tangent vector like this, what we can find is the so-called tangent plane, okay, because right now, as you can see here, you can have a small plane, okay, that is touching or tangenting to this surface at this particular point, and this plane here, the green one, the plane here, have this gradient of f, okay, has this gradient of f at its own normal to this plane, right, because it is perpendicular to this tangent vector, okay. So to find the tangent plane to the surface f of x, y, z equals to k at this particular point, then it just simply using this formula, because here is a normal vector on each of the component, right, because we talking about the gradient of f. So let me just write down it again, that the gradient of f is simply f sub x, f sub y, and f sub z in each of the component, right? So here it is a normal to the tangent plane, okay, this is a normal to the tangent plane, so we just get this normal component right there, and then you multiply, or actually you dot with the x minus x0, y minus y0, and z minus z0, and because they are normal to each other, then the dot product equals to 0, okay. And another thing that you need to know is the so-called normal line, okay, a normal line to S at P. It's just simply a straight line that passing through that point P and perpendicular to the tangent plane. So what does this mean? So the normal line is just the line that have your P as a passing point and has your gradient as a parallel, the vector that's parallel to, okay, and whenever you have your point that's passing and the vector that's parallel to that line, you can just simply go ahead and find the equation of the line, right? So let's look at one example. It's just an easy example. This one is your capital F of x, y, z. Let me just write down right here, okay, and you need to find the equation of the tangent plane and also a normal line, okay, at this point for the ellipsoid, okay, for the ellipsoid. So what we have to find is just simply the gradient of the f, right? So the gradient of the capital F is just simply the f sub x, which you have 2x over 4, so you got x over 2, and then the rest will be 0, and f sub y, which is 2y, and your f sub z, which is 2z over 9. Okay, and what we need to find also is the gradient at this particular point. Okay, when your x is -2, your y is 1, and your z is -3. So you have -1, 2, and -2 over 3 as your third component. Okay, so the tangent plane, okay, it's just simply the plane that contain this point, okay, and having a normal as your gradient f. I'm sorry, just to be particular, is a normal is a gradient of f at this point as well, okay, at the point that is passing through. So it means that the tangent plane is just simply using this one, okay, and then x minus the point that it passing through, which is now negative, so it is positive 2, I mean plus 2, and then at 2, okay, this second component of your vector, and y minus 1, and the third component of your vector, and z minus -3, so it's a z plus 3 equals to 0. Okay, it's not that difficult, right? And then the normal line, a normal line is just this line, I mean it's just this particular line, okay, the line is passing through this point, and also having your gradient, the red one, as the vector that's parallel. So what kind of equation that you like to write down? So just getting a review. The first one, if you want in a vector form, this is very easy, right? It is x, y, z equals to the point that passing through, which is this one, and then plus the vector that's parallel, and multiply by t. Or if you want to do a parametric equation, so you got x equal the point, and then the vector t, y equals the point, and then the vector t, and z equals to the point, and then the vector t. Okay, just like that. Then if you want to find a symmetric equation, you have x minus the point, so plus 2 over -1 over the vector, y minus the point, and then over a vector 2, and the z minus the point, so it becomes a plus over -2 over 3. So that will be your equation of the normal line to this ellipsoid at this particular point, -2, 1, -3. Okay, so we are going to finish this video clip right here, and this one will be the last video clip for your section 4.6. So next we'll see you on 4.7. See you then. Bye bye.